All right, good evening, class. So let's start. So today we're going to talk about decoupling control. First of all, let's be very clear about what is a coupled system. So the coupled system is a unique feature of the system where you have multiple inputs and multiple outputs. Okay. Like I said, right, for this module, you are going to learn many design techniques for the systems where you may have more than one inputs and also more than one outputs, so which make this course different from another one. Computer control. For computer control system, the main focus is on the single input, single output. Okay. Now, if you look at the, let's say this is a boiler, right? Try to boil the water, and then you try to monitor two outputs. One is the temperature of the water. The other one is the water level. So there are two outputs. Let's say you have two inputs. One is the heater. Okay, the other one is the water supply. Okay. If you look at this system, right, there are two inputs and two outputs. Okay, let's analyze the effect of the input. For example, if you look at the heating, right, this input, does the heating affect the one of the output, the water temperature? Of course, right? Of course. That is the main contributor to the temperature. Then how about the other output? Does heating affect the water level? Actually, from physics, you know, right? Also, when the temperature change, the volume of the matter will also change, right? So it also affected the water level, but of course the contribution is kind of minor. Okay, and then if we look at the other input, the water supply, right? The water supply will be a main contributor to the water level, and also it will affect the water temperature in the boiler, right? Okay, so that's what we call a coupled system. There are multiple inputs, and the output is affected by both the inputs. And because of the interaction between the loops may cause the difficulty in operating, and also for the designing of the control systems, usually it is more difficult for design a controller for the multiple inputs and multiple output system, right? Okay, now let's try to analyze the coupling from the mathematical point of view. But let's just look at the state space model. By this time, we are trying to, because right, the state space model itself like give you the relation between the state and the input and also the output. But for coupling system, we're mainly focus on the interaction between the inputs and outputs. That's why here, so we are going to use the transfer function. Okay, so how are we going to get the transfer function? First, right, so we need to get a solution. But of course, you know, since you are already, you know, at this stage, you know the solution to this linear equation, right? In part one, you are all familiar with that. But do you know how to derive this solution? The simple way, right, you can apply the Laplace transform. Okay, if you apply the Laplace transform, right, the Laplace transform can convert the differential equation into an algebraic equation. Okay, the derivative, right, in the S domain becomes the S times X minus the initial condition. Okay, and then from this one, you can get try to get the solution of the X state in the S domain. Okay, So put this on the left side, this on the right side, right? You get this equation, and then you try to solve xs, right, from this one. Okay, and once you have x, then you get your y, right, the output. And clearly from this expression, you can say that the output is affected by both the initial condition and also the input. So this response due to the initial condition only, we have a name called zero input response. So that's the response. When the input is zero, you may still have some response due to the non-zero initial condition. Okay. Then this one, we call it zero state response. That is where the initial state is zero, but the system responds to the input, right? Because the system is linear, right? We can write the response into the summation of those two terms. Okay, and I think one student sent me email asking me why when we try to evaluate the step response, we will set the initial condition to be zero, right? That is because by definition of the step response, okay, we are looking at the output when the input is a step, while we don't consider the effect of the initial condition. So when you try to look at the step response, right, remember you set the initial condition to be zero. That is for your mini project. Okay, and when you look at the stability, right? When you look at the stability, mainly you are looking at how the system responds when the initial condition is not zero. You have to look at this term. Okay. And this is what we call the transfer function of this term. So if we are only interested in the response of the system due to the input only, right? We ignore this part. Okay, we only look at the second part, and then this term will say, right? This one we can rewrite in this as a transfer function. So the output will be a transfer function times the input. But of course, if you have a multiple input and multiple output, then we will have a transfer function. This will be a transfer, not just one transfer function, but will be a transfer function matrix. But always, you do keep in mind that the outputs are affected by both the initial condition and the inputs. When you do the mini project, right, you will observe those effects by yourself. Okay, so this is where we are. Right, we have obtained the transfer function, and we know that transfer function now for the multiple input and multiple output will be a matrix. If there are n inputs and n outputs, right, the number of inputs equal to the number of outputs, right, this matrix will be a n by n square matrix in general. So if we write down the expression for all the outputs, right, it will be in this form. You can say that the y1 will be affected by u1, u2, right, all the inputs. So the output, second output will also be affected by all the inputs together, right? That is what we call, right? That's what we call a coupled system. If we look at this matrix, right? If we look at those GIGI, those non-diagonal terms, if any one of them, right, is not zero, so the system is called coupled. Since the J's input will affect not only the J's output, will also affect the I's output. Okay, so one input may affect multiple outputs. Now, then, what is a decoupled system, right? The decoupled system is a very special case where that for that transfer function matrix, only the diagonal terms are non-zero. All the non-diagonal terms, right, are zero. For Gij equals zero for all I not equal to j, which means that the I's input only affects the I's output. So if we write down the expression individually, right, we say the first output, right, is related to the U1 first input. The second output is related to the second input. So, or in other words, right, that one input is affecting one output only, right? Of course, this is a very special one, right? Now, if we draw this block diagram, easily you can say the relation. So there is some direct relation from the first input to the first output, second input to the second output. So one input affects one output. If you look at this one, immediately you can say for the decoupled system, we can, when I look at the how we change the response of the output, right? I can ignore the other input, right? I can just focus on one input. So essentially, just if I only look at the first input and the first output, it becomes a single input, single output system, right? The multiple input, multiple output system becomes a collection of M single input, single output system. Then, if we compare the decoupled system and the coupled system, which type of system is easier to control? Of course, decoupled, right? Because you have learned so many things about, design a controller for the single input, single output. You are very familiar with that, right? If you only look at one input and one output, actually, you know all the techniques. You can do the servo control, right? You can track any type of reference signal so far. Okay, so you have learned that in chapter 9, right? Okay. So easily we can say, because now we can treat the MO system just as a many single input, single output system, right? And also, if we look at the implementation and the operation from the operation point of view, right, you have a system in running now. You say, okay, I want to change one of the output. Yes, I want to change the first output, but I want to keep the other outputs the same. For the decoupled system, what you need to do, you only need to change the first input, right? Because that input will affect the first output. You don't have to change other things. Okay. Instead, for a decoupled system, right? For a decoupled system, if you want to change, for a coupled system, if you want to change the one output, actually you have to change probably have to change all the inputs, right? And also in a very complex way, such that only the first output will be changed, but the other outputs will keep the same. That will make it very complicated. So this is the beauty for property of the decoupled system, right? When we want to change one output, we only need to tune one input. Okay, so that is why today we want to spend some time on how we try to achieve decoupling for our coupled system. Okay, here again, let's look at the practical process control system. We call it distillation column control. Okay, here let's show a short video clip. If you go to some chemical plant, you may look.
One of the key elements of many process plants is a distillation system. It's important for operators to understand how distillation systems work, because it's part of their job to make sure the systems run properly. The purpose of any distillation system is to separate a liquid mixture into two or more components. The separation takes place in a distillation column or tower. The liquid mixture is called feed or charge, and the components into which it's separated are called cuts or fractions. Let's take a look at a simplified representation of a distillation system. In this example, the feed is stored in a tank. During operation, a pump is used to move the feed from the tank to a preheater. In the preheater, the mixture is heated under pressure to just below its boiling point. The pressure in the tower is lower than the pressure in the preheater. So when the feed enters the tower, it starts to boil. The vapors from the boiling liquid, which primarily contain the lighter components in the feed, rise in the tower. The remaining liquid, which consists primarily of the heavier components in the feed, moves down the tower and collects at the bottom. Some of this liquid is drawn off as the bottom's product, and some of it's routed to a device called a reboiler, which is connected to the bottom of the tower. The reboiler is usually a heat exchanger that's designed to vaporize the lighter components that remain in the liquid from the bottom of the tower. Vapors from the reboiler, or in some cases a mixture of vapors and liquid, re-enter the tower. The vapors then rise up in the tower. These vapors and the heat they contain are often referred to as boil-up. The hot boil-up provides heat that's needed for the distillation process to take place in the tower. The vapors that rise up in the tower are routed to a condenser. The purpose of the condenser is to cool and condense the vapors into liquid. From the condenser,
all right, that just gives some idea about the distillation column. Basically, try to separate the components from a mixed liquid, right? And then because of the evaporation temperature of the components are different, right? You can use the this process to separate. For this one, you can say there are two. We can say there are two inputs here. This is the boil up or heating, and then there may be some reflux from liquid. And then we will try to monitor the concentration of the components. There may be one is on the top, the other one is in the bottom. Okay, and of course, this is a distillation process that this one is well started because it's very important, right? And then it's an important subject for process control. So a long time ago, people have already derived the transfer function, which show you the relation between the input and output. Okay, this one XD is the mole fraction, which means that's the concentration of the methanol in the top. In the top, SB is the concentration, right, of the methanol in the bottom. So there are two outputs, and the two inputs are so R is the reflux flow rate and F is the steam flow rate. Clearly, you can say that, right, this transfer function is clearly a coupled system, right? The inputs affects both outputs. Okay, for some of maybe if you're not familiar with the transfer function, okay, here you have this exponential term that will describe the time delay. Okay, then okay, the control requirement is that we will try to decouple the system, right? We'll try to decouple the system such that we can control those two outputs independently. Okay, and then the solution will be given. So let's first try to get some idea on how we can decouple a system. Okay, what is decoupling? Right, from the discussion, now you are clear that decoupling control is trying to decouple a coupled plant such that the feedback system is decoupled. Why is decoupling useful? Of course, mainly is for practice for easy operations, right? If you want to change one output, you only need to change one input. So today we're going to study how to decouple. There are two schemes. We can either do it with the state feedback, or we can do it with output feedback. So the first one, you need the state space model. The second one, you need the transfer function matrix. Those two approaches are different ones. Okay. Let's start with some simple case. Then we will try to figure out the solution for the general case. Now, this is a simple example of a MIMO system, right? There are two states, X1 and X2. Now I make it simple, right? Because I want to get the idea clear. The output is just the state. You can say the related, the C matrix is identity matrix, right? Output is the state. There are two outputs corresponding to the two states. So if we get the transfer function, right? If we get the transfer function clearly, So this is the way you compute the transfer function of this A, B, C, right? You put it in because C is identity matrix. Then you get those A, Si minus A is this matrix. You get the inverse of that. And then this is B. Okay, the second one, this is how you get the inverse, right? You get the determinant. This is the determinant of this matrix, and this one is the aggregate matrix of this one. Okay, and then finally, we will end up with this transfer function matrix. Clearly, you can say because of those cross terms, right? Those non-diagonal terms are not zero. Therefore, it is a coupled system, right? Okay. This one already gave you the answer. So now, what's the objective? Okay, we will try to, let's say, actually, for this coupled system, we can design a state feedback control in this form, okay, such that the transfer function matrix from the reference signal from R to Y will be a very simple one like this. So it's a diagonal one, it's decoupled, right? And also the transfer function is very simple, it's just an integrator. Okay, let's see how this can be done. If we look at the final transfer function, right, from the reference signal to the output, remember that output is the state, right? So we can write out the final form of the state space model is just x dot equals R. So x dot, this is the output equals the reference signal, right? That's how you get this diagonal, right, single integrator. Okay? Okay. Now, if you look at this one, you may wonder, is that really possible? Right? Remember, we normally when we talk about the state space model, we have this x dot equals ax plus bu. Here, it's like, you know, a equals 0, right? There is no ax. There is only u, right? R. So, well, which means in the state space model, the term corresponding to ax completely vanished, right? There are no state variables on the right-hand side. We need to make all the state variables disappear on the right-hand side. So how is that possible? Okay, now let's just write out the equation. This is the original equation of the system, right? Okay. So what we try to achieve is simply, right, we want to make the right-hand side to be 0. Okay. Then, okay, just say, okay, we try to figure out what is the input U1 and U2 to make those two equations equal 0. Right? So you look at this. There are two equations, right? There are two input. Is it possible to choose proper values of the input to make this happen? Of course, right? You can do it. You can easily have, okay, the input, first input equals x1, second input is minus x1 minus x2. Is that clear? Right? Okay. So you say, hey, this is simple. In this way, right, we already designed the minus kx. So the input is a feedback, but now let's go to this part, right? How we go to design the f. We know that with the state feedback we already have, we plugged in, right? This minus kx to a minus bx, a minus bk, that part is already 0, right? So actually we are left with the b times f times r. That is the closed loop equation, okay? And the objective, right, we just need to design this f such that this one is an identity matrix. You can say, okay, p times f Is this this is B, this is F. I want to make it into an identity matrix. I can easily get F, right? So you can say the problem can be solved. Of course, we require that the B has to be non-singular. If we require B, this input vector matrix, right, that one, to be non-singular, it just means that inputs will affecting the outputs independently. If that B vectors is a singular matrix, it just means those two vectors are related to each other, right, which means that the inputs will not affect the outputs independently. Okay, let's summarize what we have learned so far. So when the outputs, right, correspond to the state variable, which means the states are outputs. So how we can achieve this decoupling actually is very simple. Okay, we say, okay, we apply the state feedback. So we plug it in, and we just try to make this A minus BK to be 0. Right, we put this A minus BK to be 0, and we put this B times F, this one to be identity matrix. So therefore, how are we going to design the K and F? So from the first equation, we can design the K. From the second equation, we can design the F. Now, so this is the case where you have to design both K and F. Okay, to solve the decoupling problem. For the power placement or for LQR, you don't have to design F. That's why you can just put F as the identity matrix. But here for decoupling, right, you have to design your F properly. Okay. Now, if you look at the solution, right, there is a critical condition that the B matrix has to be non-singular. Okay. Now, you may wonder, do we really need that? So let's say, what will happen if the B matrix is singular matrix, like for this one? I put it as a very simple singular matrix. So 1, 1, 1, 1. And then let's try to achieve the first goal. Let's say I try to design purely state feedback minus Kx, right? Such that the right-hand side disappear. Then what we want to achieve is that we want to find out U1 and U2 to satisfy those two equations. If you look at those two equations, is it possible to get a solution? Right, easily you can say, right, because this one have U1, U2, this one have U1, U2, but this one is X2, this one is X1 plus X2, right? So you cannot get a solution, okay? So that's how you can say there is this one, the input matrix has to be non-singular. That's very important. So if B is not full rank, then the inputs are not affecting the system independently. So of course, roughly speaking, you can imagine if the inputs, let's say you have two inputs and the two outputs, if the inputs are not affecting the two outputs independently, you cannot design a system such that one input affects one output, right? Because those two inputs are coupled together. Okay. So that's just the motivation for you to say how we can get the solution for the decoupling system, but we have to develop a general method, which can handle more complex and more general case, because, right, in reality, the outputs are not the state variables, right? So normally, the number of the outputs are much less than the number of the state variables, right? Okay, so we consider a system. So now we have this standard of ABC. Okay, we get this is how we can get the open loop transfer function with ABC. I just show you right at the beginning to get this one from the Laplace transform. Okay, this is the open loop transfer function, right? Now, what do we try to achieve is that we try to design a state feedback. We want to design K and F such that the closed loop system, right, of course, becomes this one. This is the equation for the closed loop system, and the transfer function matrix of this closed loop from the R to Y. Okay, this is, we can get this form. Okay, also this is the formula, right? Because actually follow this formula, right? Is the C times the SI minus this matrix, the system matrix, because the matrix becomes change from A to A minus BK, right? That's how we get this transfer function for the closed loop. Now, the objective is we will try to design K and F such that the closed loop transfer function matrix is a diagonal matrix, right? If it becomes a diagonal matrix, then the closed loop is decoupled. Okay. So mathematically, how are we going to solve this problem? First, we have to find out how the open loop G is related to the closed loop. Okay, let's just review what we have learned in the past, right? When you were undergraduate, if you look at a single input, single output system. So how do we get the closed loop transfer function from the open loop? Okay, here is a reference signal R, this is Y. Of course, here we put our transfer function. And then let's try to derive the transfer function from this algebraic operation. Okay, so relation between the input and output is by G, right? Y equals G times U. Then we also, how about U? We say the U equals the error signal E. E is Y, right? R, E is R minus this signal, but this signal is K times Y. So therefore, let's plug it in. So it's G times this one, R minus KY. From this one, so we get the closed loop transfer function, the H, the Y over R, right, is this one. So, okay. And this is what we have learned when you are undergraduate, okay. And also, right, this is the basic configuration for a feedback system for negative feedback. If you have a loop like this, right, this is the formula. And the G is called the feed-forward transfer function, which means if there is no feedback, now this K times G is the open loop transfer function, right? Then you may say, why we call it open loop? We have a closed loop, right? The open loop means you make it open, right? You make it open. It's a closed loop if you disconnect that and then you make it open. If you make it open, that will be the transfer function right from this input to this output signal here. That is G times K. So that's why we call this K times G as open loop transfer function. And this is the formula, right? Is the feed forward over 1 plus open loop. That's how we get the transfer function for the single input, single output. Okay, then we want to say, can we get a similar formula for the multiple input and multiple output system? Okay, let's try to do that. So here is a multiple input and multiple output. So now we use this matrix. So X is a vector now, right? So here is the matrix. So we say X dot equals A times X plus B times U, right? This is how we get those block diagram. Okay, this X times C times X, you get Y. So here, the input is the minus K times X plus F times R. Okay, we already know the open loop, right? So let's write down the open loop is just G times U. Now, we want to say, we want to get the transfer function. We will apply the feedback control. Minus Kx plus Fr Again, whenever you want to get the transfer function, right, you need to use the Laplace transform. Okay, so the Laplace transform on both sides, we get u equals minus kx plus fr. Here, this relation, there is no derivative. Okay, and then for the closed loop equation, right, we plug this u into this original equation, right? This is the closed loop model, and then we apply the Laplace transform, okay, and then we can get the x. So here, of course, I skip some of the steps. Basically, you know, the x start with becomes s times x, right? So that's how you get those s. You know, I minus this matrix, you get the inverse of that. Then, but in this derivation, you notice that there is no initial condition, right? Whenever you try to derive the transfer function, you always assume that the initial conditions are zero. You don't need to consider that. So you get those x. Then we can get the transfer function. So y equals g times u, right? But g is, now this u is fr minus kx. Then we plug in the expression of those x. We get this form. So finally, this is the expression of the closed loop transfer function. So we say how this closed loop transfer function can be expressed by the open loop transfer function will be in this form. But if you look at this form, so just to remember that for the single input, single output case, we have a formula where the transfer function is supposed to be the open loop transfer function, right? The feed-forward transfer function over 1 plus open loop. Okay, here we say, if we look at this middle term, right, it does not look like, right? It does not look like the form in the single input, single output case. But actually, we can change this expression to a more familiar one. Okay, here, this is what we want to prove. So we have already derived the first equation, that is the closed loop transfer function. Okay, now we want to express that into this form. But this form actually bears a similar relation as the single input, single output, right? If you imagine this, the inverse of this one is like a division, right? So this identity matrix is like a 1, right? So in the single input case, it's a 1 plus, this is the open loop transfer function. Okay, but let's try to prove this. Okay, we already know how to derive the first one. So the only thing we need to do is to show those two matrices, right, are the same. So here, this matrix, right, this matrix in the middle equals the inverse of this matrix. It looks a bit complicated, but remember, right? Let's say if you are taking a course in linear algebra, right, and then you want to prove this kind of problem. A matrix equals a inverse of another matrix. So what is the SOP? So what is the standard operation procedure to solve this kind of problem? You want to prove one matrix equals the inverse of another matrix. What you are supposed to do? Right, you just multiply them, right? You just multiply them. So you say, I just need to show this matrix times this matrix equals identity matrix. Right, that will simplify because the inverse of the matrix, right? Inverse of our matrix is harder to do, but do the multiplication of two matrices is much easier. So therefore, let's try to show that. Okay. So let's expand on the left side. What we have. So the first one, right, is this one, this two matrix, right? Those two terms times the identity matrix, right? We get this I identity matrix minus this matrix. And the second one is this one multiplied by the second matrix, right? That's how we get those two terms. Okay, so this one times this one gives you this term, and this term minus this matrix times, right, B, right, times K times this matrix. That's the most complicated one, right? But again, you are supposed to show, right, this one equals identity matrix. Which means, right, everything here supposed to be cancel out each other, right? But the next step is not trivial. It needs some clever thinking. Okay. Since we don't have much time, I'm just going to show you the next step. The next step, what you need to do is to manipulate this matrix. Okay. Now you are saying, okay, what is here? So here, this one we'll put as identity matrix. Okay. So what is this identity matrix? This identity matrix is this Si minus A. So this one is S minus A times the inverse of Si minus A. That will be the identity matrix, right? Okay. Now you say, okay, this one is Si minus A, but I will rewrite this Si minus A in terms of Si minus A plus Bk minus Bk. Of course, why we're doing this, because we want to manipulate this form such that you can clearly see how it can cancel out the other terms. But first of all, are you clear about how you can rewrite this one matrix in this whole thing? Is that clear? And then, okay, you copy. Okay, you copy those two terms. Done. Now it should be clear how those two terms can be cancelled out, right? The first term, right, is just this one here, right? You can say this matrix, the inverse of this matrix, times this matrix, that will be identity matrix, right? Times Si minus I, the inverse, that actually corresponding to this matrix to be cancelled out. Okay. Then the second matrix is just this K, the inverse of this matrix, times Bk times Si minus A inverse times B, that corresponding to the second matrix, and then those two terms will be cancelled out. Okay. Okay. So therefore, we know, okay, those two terms cancel out, then therefore eventually we have this identity matrix. Okay, and then we have proved, okay, the relation between the open loop transfer function and the closed loop transfer function, right? Actually, this is the formula. This is the formula for the single input, single output case, which you can say they are very similar to each other. Here we have 1 plus the open loop. So here actually we have this, right? The inverse of this I corresponds those K, times this one X, actually that corresponds to Si minus A inverse times B. That is the open loop. All right. So this is the formula we're going to use. for the decoupling problem. Okay, and let's take a close look at this matrix. Remember, at the end, what we want to achieve is that we will make this closed loop matrix to be a diagonal matrix, right? If this one H is a diagonal matrix and all the elements are non-zero, of course. If that's the case, can we conclude that this H is non-singular? Of course, diagonal matrix, right? Or non-zero. Okay. Okay, just look at H is a matrix, G is a matrix. So this one, of course, is a matrix times another matrix. If H is non-singular, how about this G? Do we require G to be non-singular? If you have a matrix, right? If which means this whole thing, right, is 4 rank. Each element has to be 4 rank, right? From the linear algebra. So G has to be non-singular. Okay? Okay, just say, okay, that's it. For your information, in linear algebra, if you have a matrix can be expressed as B times C, right? The rank of A, of course, right, will be less than or equal to the rank of B and the rank of C. Okay, so therefore, if this is 4 rank, then B and C have to be 4 rank. Okay, has to be less than or equal to the rank of B, right? Or the rank of C, the minimum of that. Okay, this is just from the linear algebra. Okay, so which means okay, every element has to be non-singular. From that we call right, G has to be non-singular. Actually, that is the key condition for decoupling. Which means that your original open loop transfer function has to be non-singular. It means that the input has to be affect the output independently. In the illustrative example, right, we assume that the inputs correspond to the state variable, which means the C equals identity matrix. Then we end up with the condition that B has to be non-singular to guarantee that G is non-singular. First of all, if you look at, okay, we need to make sure this G to be non-singular, right? Now this G is expressed by C times the matrix times B. To assure this G is non-singular, do we require B, C and B to be non-singular? Yes, I just show you, right? Just show you for linear algebra, every element in that multiplication has to be for rank. Okay, but that is not enough to guarantee that this transfer function is non-singular. Okay, because we have some matrix in the middle. Okay, that one. Therefore, we want to develop a condition to assure this transfer function is non-singular by checking the A, B, and C. Okay, so in the following, we want to come up with a condition to assure those transfer function is non-singular, because we know that is the key condition to decouple a system. Let's still use the previous example to show how we can check whether the transfer function is non-singular or not. This is the example we have already examined. Okay, and we already get the transfer function, right? So we know, of course, we have this. How do we check whether a matrix is non-singular or not? For a square matrix, There is an easy way, right? You get the determinant. You get the determinant. Okay, if we get the determinant of this matrix, that just this one. Of course, it is not 0. Okay. But we know this procedure involves the computing the transfer function. We don't want to do that. So let's find a simpler way. Can we do it without using the whole transfer function? Okay, then we need to manipulate the transfer function matrix a little bit. So let's rewrite this as a transfer function matrix. I rewrite in this way. I take out this 1 over s for each row. So take out 1 over s. So therefore, this one will be all the numerator will be multiplied by s. We get s squared minus s. This is s squared. So the second one also, I multiply by 1 over s, right? So therefore, all the terms will be multiplied by s. So this one have s. This is s squared plus s. Now, remember, I want to check whether this matrix is non-singular. We already showed, of course, this is the diagonal matrix. We just need to check whether this matrix is non-singular or not. Okay. But this matrix, we know that this matrix should be a full rank for almost any value of s, or for almost any value of s. So let's just take a special case where the s goes to infinity. If s goes to infinity, then actually we get, because if s goes to infinity, right, they will be dominated. For example, let's just take the limit of this one. When s goes to infinity, the dominant term is s squared, right? This one is dominant term is s squared over s squared. We have 1. So 1. This one also have 1. This one, we get 0. So this one is 1. Of course, already, right, we only need to look at this matrix. Clearly, this matrix is non-singular, right? But let's just look at those 3 numbers, or those 4 numbers carefully. Actually, we can find out, all right, those numbers actually are the leading coefficients of the numerators of the transfer function matrix. So this is the transfer function matrix. If I look at the leading coefficients of the numerator, the leading coefficients for s is 1, here s is 1, here the s is 1, but here there is no s, right? That's why the corresponding leading coefficient is 0. That's how actually, that's the meaning of those 4 numbers. So from this example, we see it turns out we only need to compute this matrix, right? Instead of using the transfer function matrix directly. Since only the leading coefficients of numerator are needed, we can compute them using the matrices A, B, C without using the complete matrix, the transfer function matrix G. Okay, we're not going to use that way. Only want to find out a way, right? Come up with algorithm using only the A, B, and C. Okay. So we're going to develop a systematic way to compute the leading coefficients of the numerators of the transfer function. Okay, because once we do that, we will write the transfer function in a very special form, such that we can get the solution for the decoupling problem. In order to do this, okay, we need to introduce one important concept in transfer function. We call the relative degree. So normally, relative degree was not needed in the courses in undergraduate. Probably this is for many of you, probably this is the first time you encounter this concept, but the definition is very simple. Okay, we know that the transfer function, right? The transfer function can be expressed as a numerator over a denominator, right? The numerator is a polynomial, the denominator is another polynomial. We know the degree of those polynomials, right? Here in the denominator is n, for the numerator the degree of the polynomial is m. So those are the degree of the denominators and the numerators. But here we're talking about the relative degree. So the relative degree is just the difference, right? The difference of the degrees between the denominator and the numerator. So that's how we define sigma equals n minus m. Is that clear? So that's why we call it relative degree. Okay, now we call the definition of the transfer function. Last time we mentioned the proper transfer function. That's where the degree of the denominator has to be bigger or equal to the degree of the numerator. In terms of the relative degree, it means that the relative degree cannot be negative, right? It has to be positive or equal to 0. Okay. Now, of course, here when we write out this transfer function, right? Always, if we have Rs to the power of m, right? If the degree is m, means that this term Bm, that coefficient cannot be 0, right? That is what we call the leading coefficient. If that is 0, right? If this is 0, actually the degree is not m, well, it should be m minus 1. Okay, so the leading coefficient is important, cannot be 0. Okay, now here comes the interesting thing. If you look at this expression, right? Of course, here I just try to I just take out Bm as Bm times S to the power of m. I take out the first term, right? And then therefore, because I take out this one, if now it only look at this one, the numerator, right? Of course, this one in the bracket, inside the bracket, it becomes 1 plus. Now this term, I take out s to the power of m, of course, that becomes Bm minus 1 over Bm. And here, right, s m minus 1 over s to the power of m, that is just s inverse. Okay. Now, this term, right, this term, of course, becomes B naught over Bm times s to the power of minus m, right? That is the numerator, because I take out this Bm times s to the power of m. Now, if I look at the denominator, let's try the same thing. Let's try the same thing. I take out Sn, s to the power of n, then the denominator becomes a polynomial of S inverse, right? It's 1 plus m minus 1. So because take out this s to the power of n, this will just be s to the minus 1. Then the second term will be m minus 2 times s to the power of minus 2, right? And the final term is just a naught times s. So I think this one is clearer from this. Okay. Now, and then, right, and then, okay, I just merge those two together. That becomes Bm s, right, minus m minus n. It is n minus n, but I just want to, because I want to write it as so this is a positive number, a relative degree, so minus sigma m minus n is the relative degree. So finally, I will get this one. That takes care of this. But of course, what is not clear, right? What is not clear is this term. Okay, this term you say That may not be very obvious to you, right? Of course. This is the original transfer function. We have two polynomials, right? One is the numerator, the other one is the denominator. How come in this expression we only have one polynomial? And also the polynomial, you can say that I skip many terms because this is a polynomial with an infinite number of terms. Okay. Okay. Then how do we get this one? This one is done by what we call the long division. So what is long division? I will give you one example. So for example, here, this one, let's say this is the numerator and this is the denominator. Here, one, let's say just one minus. Okay, and then how do I change this expression in terms of one polynomial with infinite number of terms? And we call long division, right? Is the division you have learned a long time ago. You do something like this. You do the division. Okay, you do the division. You say, okay, and of course, I want to make this one, right, have to match. So I will take first. I take one. So one times this. So we get okay one. Okay, then I subtract. I get 2s to the minus 1, right? And then you say, okay, I have to match the 2 to the s to the minus 1 here. So what should I add here? Should be 2s minus 1, right? Such that this one becomes 2s minus 1 times minus 2s to the minus 2. And I do the subtraction. Then I get 2s minus 2. Okay, and then you say I have to add another term. 2s minus 2. Of course, it will never end up. In this example, it will never end. That's how you can express transfer function. Well, with two polynomials, you can use just one polynomial. Of course, there is a catch, right? This polynomial involves an infinite number of terms. Is that clear? So this procedure is what we call long division in English. Long division. So finally, we have a different way to express the transfer function. If we use the relative degree, right? If we use a relative degree, actually I can express as bm times s to the minus sigma. Sigma is a relative degree, and then times a polynomial with infinite number of terms. This polynomial is a polynomial of s to s inverse. And any transfer function can be written as one polynomial with the leading terms, which involves the relative degree and the leading coefficient. Okay, is that any questions on how we can write the transfer a different way? And of course, probably this is the first time, right? You count while we do this way. It's just for the purpose of solving the decoupling problem. Okay, and there is of course there is a certain advantage in doing that. Okay, Any questions? So if not, let's have a break, right? And then we will show you how we can do this for the general case. We will do the similar thing with transfer function matrix. Okay, let's have a break, then we will continue. All right, welcome back. Right, as I just showed you, right, in the first half, how we can express a transfer function as a polynomial with infinite number of terms, right? We don't use two polynomials, we just use one polynomial. Okay, in the next we will also try to do the same thing for the transfer function matrix. So this is the transfer function matrix. I want to express this in terms of a polynomial of S inverse. Okay. So how are we going to achieve this? First, let's look at this transfer function matrix row by row, right? I mean, C is a M by N matrix, C, because there are M outputs, right? So there are N rows. A is a M by N matrix. So therefore C is M by N. Now we partition the C into M row vectors. So C1 transpose C2 transpose each are row vectors. So there are M of them because there are M outputs. Then those G, okay, can be break down as N rows, right? Each row, right, can be written as individual C vectors, right? C1 transpose times this Si minus B inverse times B. Okay, similarly for the others. So therefore, this transfer function matrix can be expressed as n row vectors. Okay, but each row is a function of S. Where we want to express, right? We want to express this transfer function in terms of the polynomial of S inverse. You will wonder where, right? Where do we find that? Of course, we have to find a way to express this one, the inverse of this matrix, right? The inverse of that matrix, that is like a division. Therefore, the question becomes, is it possible to express this one, Si minus A inverse, using polynomial? How do we handle this kind of problem? Right? Whenever, let's say you face such kind of problem and then you have no clue, always, right, a good lesson for you is that you try to figure out the answer where for the simplest case. So what's the simplest case? That's where A is not a matrix. It's the A is a scalar. For example, right? Let's say 1 minus X inverse. So X is a scalar or is a 1 over 1 minus X. Can you express this fraction, right, by a polynomial of X? Right, okay, Taylor series. That's correct. You can do it, right? Taylor series. From Taylor series, you can do it. Of course, here since I just showed you the long division, this one you can also do it by long division. You can say you do it by long division. The first term is 1. So you get X. So therefore the second term is X. That's how you get the third term is x squared. Right? You can see you don't even need to use Taylor series. You can use long division. You can also do that. Okay. But anyway, so you can see it is possible. Huh? It is possible. Okay, good. Then okay, once you know this formula, right? If you have some other things like y minus x inverse, of course you can just do some manipulation because you want to use this formula. Right? You take out this y, so in the bracket becomes 1 minus x over y inverse. Then you apply this formula, right? Then just say, okay, this just x corresponding to this one, x over y. So you get 1 plus x over y. So it's a polynomial of x over y. Is that clear? Okay. Now, so in the same way, if you have a matrix, x is a matrix, I take out those S inverse. So inside this bracket is just a identity matrix minus A over S. This is just like a 1 minus x. So in a similar fashion, I can express this one in terms of a polynomial of S inverse. This can also be done by long division. I say that, okay? And also, you can verify that. This one, this polynomial expression is very useful for theoretical analysis, okay? Because, right? Originally we have this inverse, but now it just becomes a summation because summation is simpler, easier for you to analyze. Well, there is also another way to look at this expression. You can show that from this definition of the matrix exponential. Right? You have learned this in part 1. Now, if you take the Laplace transform of both sides, if you take the Laplace transform both sides, this one actually Laplace transform of e to the at is Si minus A inverse. The Laplace transform of 1 is 1 over S. The Laplace transform of t is 1 over S squared. Okay? The Laplace transform of this one, right, will corresponding to t S minus t. Laplace transform of this one, you get this one. Okay, that's another way to say that. But anyway, so we're going to use this one. We will express the inverse of this matrix as a polynomial of S inverse. Okay, any questions? So with this one, now we can go ahead to express the transfer function matrix as a polynomial of S inverse. So now here, the GI, right? GI is CI transpose times this one, but this one, Si minus A inverse, this one, will you replace it by the polynomial of S inverse, right? So the first term is I identity, that's why I only have CI S minus 1, right? CI times B. Then the second one, right, is CI AB AS to the minus 2. So, okay. Now, if you look at this one, we say now, because transfer function will always look at, right, traditionally is a fraction. We have a numerator denominator. And in the scalar case, we know, okay, the transfer function can be written in this way. One of those leading coefficients, right, times S to the minus sigma. Sigma is the relative degree. And inside the bracket is just a polynomial with infinite number of terms. That polynomial is a polynomial of S inverse. So if you look at for the vector case, right, this one actually is very similar to the scalar case, right? E is 4. Then we say we need to define the relative degree in a same way for the scalar case. We know that the sigma, right, S to the minus sigma, that will be the leading term of the polynomial, where of course Bm is not 0. Okay, then if let's just look at this term, let's check out the relative degree, right, in the same fashion as that for the scalar case. For example, if we look at the leading coefficients of here, of course, this is a vector. But let's say if this one is not 0, if this one is not 0, which means that the coefficient, right, for the term S to the minus 1 is not 0. If we look at the definition of the relative degree for the scalar case, that should correspond to which case? What is the corresponding case for the scalar case for the sigma? What will be the sigma if this term is not 0? What will be the relative degree? If this one is not 0, what will be the relative degree? Imagine this is just a scalar case. Then what will be the relative degree? Will be 1, right? Because that corresponding to this one will be sigma will be 1. Is that clear? So, and this will be the leading coefficient, right? Okay. If this one leading coefficient, this one is not 0, and sigma equals 1. But however, if this one is 0, right? If this one is 0, then this one of course disappear. The leading term will be S to the minus 2. You check out this one. If this one is 0, you are left with this one. Then what will be the relative degree? Sigma will be 2, right? Sigma will be 2. So we need to check out those terms, and then from that term we can get the relative degree clear. Therefore, then you can say we can find out our SOP to get the relative degree and the leading coefficients using just A, B, C. So we will define the relative degree, right? Sigma I for this ith row of the transfer function matrix. That will be the integer such that, right, will be defined such that the coefficient is not 0. We say, okay, you look at the minimum j, which makes this CIA to the power of j minus 1b is not 0. Minimum j, which means you first check j equals 1, right? Which means, okay, the first term. That's where j equals 1. Which means you look at those coefficients one by one. From the first one, right? If this is 0, you check this one. If this is 0, then you should check the next one until the non-zero term appears. Then you define the sigma I. So if the first term is not 0, the sigma will be 1. If the first term is 0, then you go to the second term, then sigma will be 2. Okay. So therefore, this is the procedure to compute the sigma r. Let's say you're looking at the ith row, right? So for I equals 1, let's say, which means C equals 1, right? C1. Then you start with J equals 1. J equals 1 just correspond to the first term. You just compute the C1 times B. C1 times B, look, is it 0? If it is not 0, you get, okay, sigma equals 1, the relative equals 1. If it is 0, right, then you go to check the second term, C1 times A times B, the second term. If this one is not 0, okay, if the second term is not 0, of course, then the relative degree is 2. If this is 0, then you move on to the third one. That's the case. That's the way you compute the relative degree. Okay, is that clear? Then you do that. You can do that for all the rows. In the calculation process, right, if you at one step, all of the vectors, say b equals 0, say b equals 0, say a square b equals 0, all of them equals 0, of course, which means the row, the whole row will be 0. For a matrix, if one row is completely 0, of course, that matrix is singular, right? Is singular. Then you know it is impossible to decouple the system. Okay, let's just work out one example such that you are clear about how we compute the relative degree. Okay. So here we have there are 2 inputs, right? 2 outputs. So therefore, there are 2 relative degrees. Okay, let's check out the relative degree for the first row. So you say I equals 1. So we take out the first row of this C. C1 equals 1.5. Then you first one just compute the C times B, C times B. This one times B. You get a vector. Clearly, right? Clearly, this vector is not 0. So if this C times B is not 0, the first coefficient is not 0, right? Then you get, okay, the relative degree is 1. Is that clear? Any questions? Okay, then you finish, right, the first relative degree computation, then you go to the second one. For the second one, you say, okay, then you take the second row of the C2, then compute what is C2 times B. C2 times B, you get is 1, 1. Of course, is not 0. Then you get the relative degree equals 1. Of course, you can imagine. Probably in many cases, the first one will not be 0, but it may happen that the relative degree, the first coefficient probably can be 0. Okay, let's look at this matrix. This is another equation this is a third order system, but you have 2 inputs, 2 outputs. You take out the first one, C1, right? C1, and then C1 times B, C1 times B, this one times B. You can see you can't have a situation where both terms are 0. If that happens, right, the leading coefficient will be 0, right? So therefore, the sigma cannot be 1. Sigma cannot be 1. Then you move on to the second term. You have to compute C1 times A times B. C1 times A times B. In this one, you get, okay, it's not 0. That's how you can confirm that the relative degree for the first row is 2. Okay? Any questions? Then you move on to compute the relative degree for the second row. So I equals to, you get the C2, the second row of this matrix C. You get C2 times B. Now in this case, it is 1, 0. So the vector is not 0. Then the relative degree is 1. Okay? So you first get C times B. If it is not 0, right, you stop. Okay, if it is 0, you compute C times A times B. If it is 0, then you have to move on to the next step, or say to the times A squared times B. Okay, eventually you'll get some number which is not 0. But of course, it may have some, you may encounter some situation where probably all the terms are 0. In that case, right, you don't need to compute R, which means the transfer function will be singular. All the terms will be 0. Okay, now with that in mind, now here, following is a very important step. We are going to rewrite our transfer function in a very peculiar way. Now, let's look at this expression of the transfer function again. Okay, here, I just showed you right before that this transfer function can be written as a polynomial of S inverse. Now, with the help of the definition of the relative degree, because we know the sum of the terms, right, the leading terms may be 0 if the relative degree is not 1, right? Okay, so we know we have to take out those 0 terms. Therefore, let's say if the relative degree, right, is sigma I, which means, right, this one, only C times A to the power of sigma I minus 1 times B will not be 0. Any terms below that, right, C times B, C, A, B, up to C times A to the power of sigma I minus 2B, all of them will be 0. That is the way we define the relative degree, right? Okay, so therefore, let's say the relative degree of this GI is sigma I, then this one will be written. Let's explain them one by one. This is its original expression. Now we take out those terms, right? Those 0 terms until the first term, right, is not 0. Okay, that will correspond. This is the leading term because the relative degree is sigma I. All the terms before that will be 0, right? Okay, and then I take out those S to the minus sigma I on the outside. If this one is out, so this one corresponding to this term, right? Okay, because I take out those S to the minus sigma I outside, so this term becomes S to the minus 1. And then this term, right, will becomes so therefore here there will be S to the minus 2. Right? Okay, that's how we say, okay, because I take out this one becomes this one becomes this term, and then there's some other terms. Now, for all those terms, I can regroup them. S, of course, is a scalar, right? I can take out this B on the right side. Then I can also take out this A to the power of sigma I. Then this term will be still be is identity, but this one is is A to the power of sigma I plus 1. So we have A. Here we have A squared and upwards up to the infinity R. So this is how we express this one by this form. But up to here, is that clear? Any questions on the derivation here? But finally, if you look at this summation of those infinite number of terms, that actually corresponding to the Si minus A inverse. Okay, any questions? Okay, this will be the key equation to understand the decoupling. So we rewrite this transfer function using the relative degree. We rewrite finally. We write the transfer function, each row into this form. This is just like the form for the scalar case where you have this is sigma I, right? That is the relative degree. The first term, of course, that is the leading coefficient of that first term, right, for that polynomial. Then the rest of one, of course, it corresponded to the infinite number of terms, but I put them back. I put them back using the original expression of the inverse of the Si minus A. That corresponded to the infinite number of the terms, that polynomial. Okay. So somehow, but of course, at this moment, you still don't know why we are doing this. Eventually, you are going to know. But here, at least, right? At this moment, let's be very clear. With the help of the relative degree, right? We have the leading coefficient of this for the first term, which is non-zero term. This is the leading term of this polynomial. And then there are some other terms. I can write it with a compact form with the help of the expression of this matrix, the inverse of the Si minus A. Okay? Any questions? Okay. Once you understand this, the rest supposed to be easy. So every row, right? Let's just write out every row. The first row, right? The relative degree sigma 1, so it's s to the minus sigma 1. This one is c1 a to the power of sigma 1 minus 1 times b plus this matrix. So this is the second row for the of this transfer function matrix. So the relative degree is sigma 2. So s times the minus sigma 2, and this one is c2a to the power of sigma 2 minus 1 times b plus c2a sigma 2 times the inverse of this Si minus A times b. So we can just write out the expression for each row. Okay. Now, and then let's put a split, right? This one into two matrices. Okay. Then we have this diagonal matrix. Okay, each matrix you can say, right, very simple terms. Those are s to the minus sigma 1 is to s to the minus sigma 2. You can verify, right? If you do the computation of this matrix, right? Let's say this one times this one, right? You will get this term, right? And then this row times this vector, column vector, right? You will get this one, right? Okay, so that's why we can write this matrix as a multiplication of those two matrices. Okay, and the next, right, we try to write this second matrix as summation of two matrices. Clearly, right, we can group those together into one matrix, those terms together as one matrix, and then those together we can write into this matrix times the inverse of this matrix times b. Okay. So finally, right, this G, the open loop transfer function, can be written as this matrix. This in terms of this diagonal matrix. Those diagonal terms are related to the relative degrees of this matrix. And then we introduce two matrices, this one and this one, B star and C star. Okay, now the definition of the B star, like given previously, right, is just we know those are the leading coefficients of the polynomial, and we know all of them are not zero. All of them not zero. C star is defined in this way. This is just copied from the previous expression. Okay, but the point is that this open loop transfer function can be written in this form: a diagonal matrix, right, times this one. Okay. So this, I already give you the computation algorithm, how you define the relative degree. Because you know, when you compute those matrices, it's very important to get the sigma correct. Correct. Because once you know the sigma 1, sigma 2, then you can compute the B star. If you don't know the sigma, the relative degree, right, you don't know how to compute the B star, because B star is defined clearly by A, B, C, and the relative degree. Okay. And also here, the C star also depends upon the relative degree, right? So you have to get the relative degree correctly. The B star, right, corresponding to the leading coefficients of the zero polynomials. Okay. Now we can state the theory, right? The solution for the decoupling problem. There exists a feedback control law minus kx plus fr. We can decouple the system if the B star, this matrix, is non-singular. If that is the case, right, this is the way we can compute the game matrix. In this way, the final outcome of the transfer function of the closed loop is just a diagonal matrix, where those diagonal terms, you can look at those diagonal terms, are just the integrators. How many integrators for each one, that depends upon the relative degree. Okay, now here we comes why we want to. Here comes the answer. You will be able to say clearly why we want to put the transfer function into that special way. We spend a lot of time, right? This is the key equation to understand the decoupling. But of course, how we end up with this expression, right, that takes a lot of effort. You have to define the relative degree. With that one, you know, we have to express the transfer function in terms of polynomial with infinite terms, right? But finally, right, we can come up with this last form. Okay, but of course, like I said, right, you don't know why we did this. Now here comes let's review the purpose of this expression. We know G can be written in this one. And B star and C star already defined, right? They're all related to the relative degree. So those are the two matrices. Now, what is the objective? We know that those open loop transfer function and the closed loop transfer function actually are related by this formula. We have already proven that. So now let's plug in the expression of this open loop transfer function. It is matrix, right, with those peculiar forms, right, those integrators which depends upon the relative degree times this matrix. That is G. This whole thing is G. Now this one here is the inverse of this matrix times F. But just to make it clear, I put those F inside those inverse. Okay. So this one, we get this. Remember, right? I mean, if you do this one, you take the inverse. Of course, you have to switch the sequence, right? Will be B inverse times, let's say, if they are all non-singular, you have to do it like this. That's why I put those inside this. Okay, then this one is F inverse times this matrix. Okay, that's how we have this F inverse appears on the left side. Okay, any questions? Then we are ready to show the answer. Now, remember what's the objective? The objective is we will try to design K and F such that the final answer for this closed loop is the diagonal matrix of this one, where those diagonal terms are the integrators. The degree of the integrators depends upon the relative degree. If this one equals this, it means that we need to design our K and F such that this matrix, right, times this matrix equals identity matrix. Correct? Now, if a matrix times the inverse of another matrix is an identity matrix, what does that mean? Those two matrices have to be the same, right? So this matrix equal to this matrix. Now you look at the form of those two matrices. Now the answer is clearly in front of you, right? Tell me, how do you define your F? What is the equation for F? The inverse equals B star, right? Clearly now everything is clear. F inverse equals B star. And what is the equation for K? F inverse times K equals C star. So now you get the answer. See? Now you can say the key is to find out a way to express the open loop transfer function in this form, right? That is the step to understand the decoupling solution. Okay? We spend a lot of effort to show that. Once you have this one, then the decoupling scheme is easy to understand. Okay? Any questions? Okay, if you look at this solution, if we compare to the special case we obtained as special case, we consider at the beginning, right? We say this is the when the number of when the outputs correspond to the state variables, right? Y equals X, this is the answer. K actually equals just B inverse times A. F is the B inverse. In that case, actually, that B corresponding to the B star. Here. Okay. Now let's look at one example. This one where I will already show this one. Let's solve the decoupling problem. We try to do the integrator decouple. So we say this is the G, we get the transfer function. Right, we know actually this is a coupled one. If we look at the transfer function. Okay, and then we also for that one, we already computed the relative degree. Both of them are 1. And then we can compute the P star. Already, right, is 1.511. So we have this P star. And then we can compute the C star, right? This is C1 times A sigma 1. Sigma 1 is 1, so C1 times A. We get this row. This is the second row. That would be the C star. So we get the P star, C star. Those are just, as long as you get the relative degree correct, right? And all the answers are just the matrix calculation. Of course, in order to do that, you need to know how you get the inverse of a matrix. Then you have this F and K. You have this formula, right? You get your K and F. Actually, you can verify. This is the closed loop system. You can say that this one, right, X dot, right, does not depend upon X. But because Y, the output, right, is related to the state variables, right, in a very peculiar way, right? This one is not identity matrix, that's why here. This one matrix is also not identity matrix. But eventually, if we will compute the transfer function from R to Y, this will be the transfer function. It's an integrator decouple. But then there is a question. If we decouple the system, right, if this is the closed loop transfer function, if we look at those two transfer functions independently, integrator, but is integrator a stable system or not? Is integrator stable or not? Come on, that you should immediately give you the answer, right? It is not stable, right? It is not isotropic stable. The reason no. So what we really want, of course, we want the closed loop to be stable, right? We want the closed loop to be stable. So therefore, can we do decoupling with power placement, right? We not only decouple, also make sure that it is stable. So once we have the closed loop transfer function, right? Each individual transfer function, right? Those polynomials, you want to make it stable, not just an integrator. But you look at the leading coefficients, where the degree of this polynomial is defined by the relative degree. Then you can make them stable. Well, so how are we going to do that? It just turns out we just need to change the way to compute the C star. Okay, so therefore, here I just stated the theorem 2. We don't change the way to compute the B star. B star keep the same. It's just this one, this corresponds to the C star. But here we define it differently. So we will define this one C1 times this matrix, but this matrix is no longer A to the power of sigma I. It also involves the other powers of the A. So A to the sigma I minus 1, A to the sigma I minus 2. Okay, but those one, so how do we compute this one? That will decided by the polynomial, the closed loop polynomial for each subsystem. In the very special case, right, in the theorem 1, what we achieve is just make this closed loop polynomial for each one as s to the power of sigma I. Right? Okay. So which means in that one, actually all those are 0. So this one covers the previous one. If we put all of them as 0, actually how you compute those a to the power of sigma I? Here that corresponding to this term, right? This term will be the C1 times a to the power of a sigma 1. The second term will be the C2 times a to the power of a sigma 2. Okay. Now, okay, we don't have time to cover the how to derive this. The details are given in the lecture notes. Let's just look at the example. So previously, just to show you that one we can achieve the integrator decoupled one. But here we say, okay, look, because of the integrator is not stable, I want the closed loop to be stable. Okay, those two I want to make it. The first one is 1 over s plus 1. The other one is 1 over s plus 2. Now, of course, it is stable. So how would that affect the design? If this is a requirement, right, according to the theorem 2, okay, we still keep the same B star. We only need to compute the C star in a different way. So because this is the desired polynomial, right, it's no longer S. We have S plus 1 and S plus 2. That will change the way to compute the C star. In the previously, right, previously it's just S, so we don't have this. But here, because I have S plus 1 and S plus 2, so that will change the way up. So this one, because it's S plus 1, right, that will correspond to C1, those A plus identity matrix. S plus 2, that will correspond to A plus 2 times identity matrix. You can say the way is just, this is the polynomial, you put S equals A, right? Put S equals A. That's how you get, because this S plus 1 becomes A plus I. The second one, S plus 2 becomes A plus 2 times I. Okay? Of course, I want to mention that a common mistake made by the students in the calculation is in the, let's say in their MATLAB, they just put A plus, let's say 1 in MATLAB. If in MATLAB we do this, this 1 will be added to every element. Okay, so you have to define our identity matrix. Okay, otherwise you will make a mistake. All right, so once you do this, okay, then you can compute your K, you can compute your F. You can verify though this is A minus BK. And then you can get your transfer function, you can verify that. Okay, so for your mini project, right, let's say there is a decoupling problem. If you use the state space approach, of course you have to try to make it stable, right? You don't want to decouple it into integrators. You have to use the theorem to do that. Okay, so that finished the scheme for the state space approach. Now, let's look at another way for decoupling. How are we going to do it, right? If we don't have the state space model, instead we know the transfer function. Or sometimes, you have the state space model, but you can still use this, okay. From the state space model, you can derive the transfer function, right? And then you can follow this approach. And also this approach, right? The result from this one will be different from the one using the state space model because the idea is totally different. Actually, the solution is much simpler than the state space approach, because for the state space approach, while we spend a lot of time on try to express the transfer function matrix into a very special form, right? That takes a lot of effort because it's not a familiar stuff you have learned in the past. But for this one, right? But for this one, it is much easier because it involves something which is quite common. Okay, so what is the problem? So here, remember this Y and the R now they are vectors, right? They are not just one number. So this G is a transfer function matrix. You want to construct a controller, right? This of course is also a transfer function matrix. We try to design this K such that the feedback system is internally stable and the closed loop transfer function matrix. This actually is the expression of this closed loop transfer function matrix. Okay, you can easily verify that by doing those algebraic operations. So, but I'm not going to spend time on that. So let's move on. This is the closed loop transfer function. We want to design K such that this closed loop is diagonal decoupled. So finally, which means the transfer function from R to Y is decoupled. Okay, look at the expression of this one. So G is the open loop transfer function. K is the controller we want to design. We want to make this decoupled. H is diagonal. But let's take an inverse on both sides. If we take an inverse on both sides, right, this one will be the inverse of H. This one we'll have to take the inverse of the G times the K, but inverse will have to switch the sequence. So this inverse of GK will appear on the left side. The inverse of this matrix is just identity matrix plus GK. So eventually we get this one. This is the expression. The inverse of this closed loop equals the inverse of this G times K plus the identity matrix. The point I want to show is, you look at this expression. This is the matrix. This is the matrix. I is the identity matrix. If they eventually, the objective is to make this H is diagonal. If H is diagonal, of course, the inverse of H is also diagonal, right? If this is diagonal, we know this I is a diagonal matrix. Now, how about G times K? Can we conclude that G times K must be a diagonal? Has to be. So therefore, G times K is diagonal. Therefore, from this expression, we know that the closed loop H is decoupled if and only if the G times K is decoupled. That will simplify the design. So the problem becomes, you have a transfer function matrix, right? You design another matrix K such that G times K is diagonal. Now, from the linear algebra, right, you may quickly come up with one solution. You are given a matrix G. How do you get another matrix such that the result is a diagonal matrix? The inverse of that matrix, right? Is that the answer for the decoupling problem? We say, can we do that? Right? It looks so simple, right? Looks so simple. So you say, hey, why if this is so simple, why do we spend so much time on the first scheme? So it cannot be so simple. Huh? So let's say, what could be the problem? Right? But let's first try this out. If this is the case, so they should also work for the single input, single output case. Let's look at the single input, single output. This is G. If we take the inverse of this G, this is K. And then you will multiply them together. So we're supposed to get 1. Do I have a problem here? Are those two transfer functions, you put them together, can you cancel out all those terms, you get one? Okay, I think. Okay, it doesn't work out because you cannot simply cancel out this unstable poles and zeros in the transfer function. Not only that problem, there is also another problem with this controller. What was the problem with this controller? It's not proper, right? Not proper. What is the relative degree? -1 cannot be negative for controller, cannot be negative, so it's not proper. Of course, that is a minor issue. The issue is this. Can we cancel out in this way? So I think that is actually that is a very tricky issue when you use a transfer function. Let's just consider a simpler case where that this one is just a first order system. You design a controller, you want to make it stable. You put this, you want to cancel out S-1. The point is, okay, if you do this, if you want to get the transfer function from the R to Y, eventually, right, eventually, that will be the final answer of the transfer function from R to Y here. So what it says are those S-1, S-1 cannot be cancelled out. It will remain, but of course, still probably it's not clear to some of you why we should keep them. Okay. I don't know whether what was that explained in part 1. But I saw, okay, some of students take up another course, probably they know the answer. But for those of you who probably not clear, it's not clear when we look at the transfer function itself. But okay, let's do it. Let's try to write down that differential equation. Then you will see. Because this one here, we know this G is 1 over S minus 1. We get the differential equation and then we try to get the transfer function from the differential equation. Okay, from that one you will know that can explain we cannot cancel out S minus 1. So this K is S minus 1 over S plus 2. Because of course this U and Y are related by this transfer function. So therefore the differential equation I can write down is Y dot minus Y equals U. Right? Because it's 1 over S minus 1. Here this is R minus Y. Right? This one E signal is R minus Y times this one equals U. Therefore, in terms of the differential equation, what we have is let's write it down here R minus Y. This one is S plus 2 times U. So the differential equation over here in differential equation S times R, that is R dot minus Y dot minus R plus Y equals U dot plus 2u, right? That is the differential equation. Okay, now because we want to have a differential equation relating r and y, so here we just replace because I know u is related to the output. So this u dot is y double dot minus y dot plus 2 times y dot minus y. Okay. Okay. And then let's put those output on one side, right? We have the y double dot. Okay. So we have those minus y dot plus 2y dot. We have another minus y dot, right? That will be 2 y dot. Now I have this y, I put this aside with minus 3 y. That is the output. How about r? So r is just r dot minus r, right? That is the differential equation relating the r and y. Okay, is that clear? And then from this one we can get the transfer function. We do the Laplace transform. Then the transfer function is okay. Is y double dot, that is s square plus 2y minus 3. So r dot minus 1 dot s minus 1. That corresponds to this one. That explains that you cannot cancel out s minus 1. It can be understood from the differential equations. Okay. So which means the system is unstable. S minus 1 cannot cancel out. Okay. So from this example, we show it is always dangerous, right? If the calculation involves some unstable pose and zero cancellation. We need to avoid this. Okay, we need to avoid this because that may cause some trouble. Okay. Therefore, the answer is not as simple as just take the inverse of that matrix, because that one may lead to some complicated issue. We cannot take this one as a simple answer for the decoupling. Let's do it in a different way. So when a controller K decouples G with no unstable pose zero cancellation, just make sure there no unstable pose zero cancellation will be involved. Then the decoupled one can be stabilized loop by loop because it is decoupled. Each one is just a single input, single output system. We can stabilize it using the method you have learned last week, right? The power placement for the single input, single output. So let's just state the theorem 3. The plant is decouplable and stabilizable by output feedback if there is a controller such that G times K is decoupled. And also, there is no unstable pose zero cancellation in the calculation. Okay. Then below is the design procedure. So the decoupling problem with stability can be solved by design K in 2 stages. One is the decoupler, the other one is stabilizer. Step 1, you design KD decoupler, make the G times KD diagonal, a non-singular. In this step, KD is not required to be proper because KD is not the final answer. The second step, once you design your KD, right, then it is always to design a diagonal controller, KS, because KD times G is already a diagonal matrix, right? For each diagonal term, you design your K, the stabilizer. And the K, the final controller is KD times KS. So just make sure the final controller is proper. Okay. Then it will work. The second step, right? How do we do the second step? Right, this one you have already learned that in chapter 9. For any system, right, you can stabilize it for the power placement. So we just focus on the first step. How do we make it decouple? So, of course, we say G, the inverse of G is easy way, but sometimes it may involve unstable pole-zero cancellation, right? We want to avoid that. Then there's some other ways to make this G times KD a diagonal matrix. I will just show two ways, but there's some other ways. So for design for decoupler, suppose that this G is non-singular. Because G is non-singular, I can always write this G as this one, N is a matrix, but that matrix only contains the polynomials, not a transfer function. This D is the least common denominator of this G. You take out the least common denominator of all the transfer functions in that matrix. Of course, then all the items left in the matrix, there will be no denominator. So that will simplify the calculation for all the elements inside N, right? They are just polynomials because you take out this common denominator. Okay. If you can write this G in this form, D is the just one polynomial, N is a matrix. Now you can design this KD. If you have a matrix, you can compute the adjacent matrix. The matrix times its adjacent matrix, that will be the determinant of that matrix times the identity matrix. This is the determinant, that is one polynomial. The D is a polynomial, of course, right? And then this is just a kind of a transfer function, right? Times identity matrix. That make it decoupled. Okay. Here is the definition of this common denominator, right? You have many items. You take out the one, right, which is the least common denominator. For example, here, if those two transfer functions, 1 over s plus 1 over s plus 2, the least common denominator, of course, is s plus 1 times s plus 2. Here you have 1 over s and 1 over s squared. The least common denominator is s squared. Now about the linear algebra, right? This is well known. How you get the inverse of a matrix? You need to get the adjacent matrix, right? It's defined as the adjacent matrix over the determinant of that matrix. In other words, right, the matrix times its adjacent matrix is the determinant of that matrix times identity matrix. Of course, how you compute the adjacent matrix, right? That will, you need to compute the cofactor of that matrix. Just give you one example. This one, you first get the cofactor of this one, right? You say, okay, I'm going to get this one. Okay, you are going to get, take out those two, you get this M22, right? Okay, you say, I'm going to get this one, you get M21 minus M21. Because this is positive, then this is negative. So I'm going, I want to get this number, right? Okay, you are going to take out those two, I left with M11. Here, okay, I get this minus. I want to get this one, so this one I get minus M12. And then you take the transpose of this one. You get the transpose of this one, you get the adjective matrix, right? Okay, that's just a simple stuff from linear algebra. How you get the inverse of a matrix. But remember, even if a matrix is singular, you can still has its adjective matrix, right? Adjective matrix. It just turns out if it's singular, then the determinant will be 0. Right? Okay, if we follow that way, then the decoupler, right? Of course, the decoupler may not be proper. That's why we need the second step. So we need to design a stabilizer. For once it is decoupled, right? For each channel, we design is a single input, single output loop. Right? How you stabilize a single input, single output system? We discussed the details in last week, right? Chapter 9. Chapter 9, the servo control involves 2 parts: servo mechanism plus stabilization. Then after KS is complete, always check there are no unstable pole zero cancellation. Make sure if it involves unstable pole zero cancellation, it will not work. Now let's just show you the example here where it's give you a transfer function matrix. What is the least common denominator? S plus 1, S plus 2, right? S plus 1 times S plus 2. So if you take out this least common denominator, right, and then all the terms or items in this matrix does not involve any denominator anymore, right? That's why we want to do this. That will simplify the calculation. Simplify the calculation. We do not want to involve some, calculation which involves both numerator and denominator, right? We want to simplify that. So we are left with this one. So, okay, then we check the determinant actually of this one, the determinant of this matrix. You can check actually just 5 S plus 1 times S plus 2. Because the here is determinant of this matrix, and this D, we know there are common terms, but those common factors, they are stable, right? They are stable, so no problem. Does not involve any unstable cancellation, so it is okay. Then how about KD? KD is just the adjunct matrix of N. Here is N. So you take the adjunct matrix, you will get the KD, get those KD. And we know the final answer, the G times KD is just the determinant of this N over D. It's just one number, 5, 5. Okay. Of course, there is a problem, right? Is KD proper? Of course, KD is not proper, right? KD is not proper. So that's why we need to design the KA stabilizer and also make it proper. So we need to design a diagonal controller. Remember, the system is already decoupled, but I want to design another stabilizer. Not only stabilizer, we also try to make KD proper, because this KD is just a polynomial with a degree of 1. So if you design your KS as a controller with 1 first order degree, it will make it proper. The many ways are the simple way. I just choose one of S plus 1. Then the overall controller is a KD times KS. You can check. KD is not proper, but I multiply by this KS. This will be the overall controller. The overall controller, this K, of course, is proper. Okay? So those two are the first order controller, those two just are simple gains, right? So there's no problem. Okay. So finally, because we remember this K, G times K is G times KD, right, times KS. G times KD is here, right? Is just 5. And then this KS is 1 over S plus 1. So eventually, this will be the open loop transfer function after decoupling. Is already decoupled. In this whole procedure, do we encounter any unstable pole zero cancellation? There's no unstable pole zero cancellation, right? Okay. So therefore, no. So now finally, let's check. It's a decoupled system. We can check whether the closed loop is stable or not. Those are just the open loop transfer function, right? The closed loop transfer function is easy. We just check it one by one. For the first open loop, 5 over S plus 1 is the transfer function. We know the closed loop transfer function is L, right? The open loop over 1 plus L. So just plug in, you get this is a closed loop transfer function. Of course, it is stable, right? You have a pole of -6. Similarly, we can check the stability for the second loop. Okay. But one problem with this simple method is that the order of the decoupled system may be big. So there is a refinement of this method. So one way to reduce the order of the decoupler is to express the transfer function matrix into a different way. We don't use the least common denominator. We can use the least common denominator for each row separately. So D1, Di is the least common denominator for the ith row. In this way, we can simplify the design. In this way, we can write it as a diagonal matrix with those least common denominator for each row. Still, we can keep this matrix NR to be a matrix with the elements. Those elements are just the polynomials of S. There will be no denominators inside this matrix. Then, just as before, how we choose my KD, we choose KD just as the adjugate matrix of NR. Because NR, right, times KD, that will be the determinant of this matrix, NR, times the identity matrix, right? That will make it decoupled. So as long as the determinant of this NR and those denominators, common denominators, have no common unstable roots, then it will work. Then the final, right there, this will be the answer for the decoupled system. The answer is different from the previous one. Okay, for the previous one, all the subsystems are the same, but here, right, the subsystems are different. But it has its own advantage. It can simplify the design and reduce the order of the system. Okay, now let's use the second design for this example. If you look at this transfer function matrix, what is the least common denominator? So I have S plus 1, I have S plus 2, we also have S plus 3, right? You multiply them together. So in this case, right, this common denominator is this S plus 1 times S plus 2 times S plus 3. If I use the previous method, that will give me a system, each subsystem, well, with a degree of 3. But there are 2 of them. So it's 3 times 2, the total degree will be 6. Let's try the second way on whether we can get a simplified answer. The second way is we don't use the least common denominator of this whole matrix. We get the least common denominator row by row. For the first row, the least common denominator is just s plus 1 times s plus 2, right? If we use that one, then the first row will becomes the one is s plus 1 because the first one does not have s plus 1. I have to put s plus 1. Here, I keep the minus 1, right? Then the second one, the least common denominator is just s plus 3, right? I put s plus 3 here. Then the term, those numerators, I just keep them 5, 1. Okay? So the second step, right, is to make sure that there are no unstable post-zero cancellation, where you just compute the determinant of this matrix in R. Either you can compute it, it's just s plus 1 minus 5 and s plus 6. Of course, there will be no common unstable post-zero cancellation. Therefore, how are we going to get the KD? KD is the adjugate matrix of this matrix. Adjugate matrix of this matrix. So therefore, you take out this row, we get 1, right? This here, this one you get s plus 1, get 1 minus 5. That's how. Okay. Any questions? This is the adjugate matrix of this matrix. So this is your decoupler. And then this G times KD will be, right? This is the determinant of this in R, that is s plus 6. So it's s plus 6 over the least common denominator of the first row. The second one is s plus 6 over the least common denominator of the second row, s plus 3. It is double. But again, right, there's still one problem with this KD. What is the problem? KD is not proper, right? It's not proper. So therefore, we have to design the stabilizer. Because this KD, right, we look at the degree, right, it's a first order degree. If we just design like stabilizer with a first order system, it should work. And also, just by examining this transfer function, we notice, right, there are stable zeros. The simplest way is you design a stable pole as the same as the stable zero. We just cancel them out. Of course, that will only work for this particular one. We will check that. So if we check, we just use this is a simple solution. Okay. Then first we just check the total controller is proper or not. So K is just KD times KS. We can easily verify this matrix times this matrix. You can say now all the controllers are proper, right? So there is no problem. The total controller is proper because this is the final form of the controller we're going to use, right? Okay. Now, are there any unstable post-zero cancellation? There are not, right? We know there are not, so it is okay. So now finally we just check whether the closed loop is stable or not. We know this is the open loop transfer function. S plus 6 has already been cancelled out by the stabilizer. Okay, then you can easily get the closed loop transfer function from the open loop transfer function. I skip the details. So those are the closed loop transfer function. If you look at this second order system, as long as, because those two are positive numbers, right? As long as those two are positive numbers, it's guaranteed stable. Here we have a plus minus 4. So there is no problem. It's decoupled and the closed loop is stable. Okay. So for your mini project, right? For your mini project, you try to find out a way, right? I mean, now I give you 2 ways to design. You can try either one of them and say whether it works or not. Okay. But of course, it's a little bit more complicated, right? Because it's a 6-order system, it involves a lot of calculation. So don't worry, right? You are not going to do this kind of problem in your final exam, right? The final exam cannot be 6 by 6 matrix. The biggest matrix you are going to handle is just 3 by 3. Cannot be no more than 3 by 3. All right, so that's all for today. And I will see you next week.我把每一行的那个先提出来了。只有2的话，它那个这里面它每项都是一个多项式，没有分母，就是要求它是知道 GS。对呀，知道它，然后再看。但你看我的 example， 你的例子搞明白了就行，我不给了解释吗？对，对，你例子搞清楚啊。我的意思就是这个这样是你的，就是你把它的公分母去拿，或者说只有1嘛，对不对？然后它的这个公分母的话，它应该是加1 S 加2的话，前面还有个 S 加1，是吧？就是这样子。observer 你们现在还没学。哦，然后找这个材料，材料的话嘛，不管设计它，有时候我会得到一个6阶段式方式，然后去算6阶段式方式，然后这个时候就是到地方在随机对应，这个时候就K 化，因为 K 化它的对方每个有这个，还有50多个解嘛，还有跟那个 population 里跟那个问题是一样的。对，是63个分，对，就是说如果有一个分是大的，这个我下个礼拜会讲。这个问题也是在那个就是你要设计第一题的 K 的时候，就是对，我用那个就是找那个开林东那个对，那个找那开林东那个就是它和一个也是 determination， 然后自己知道一个 determination， 然后把这个自己写一个什么一个 form 的那个路吧，对 matrix， 对啊，比较，那比较的时候那个只有唯一解呀。我的时候你把看到那个 form 确定之后，给那个 designer 看到那个 form 拿出来，那只有唯一解嘛。就是对啊，对啊，就2乘2，对啊，对，是吧？那个可以，你不会有多个点。这个就是不是它的比赛的话呢，就是有很多种方法。它呢就是说，你可以完全用高分数，你就是你要把当然那2个就要这个参数。 们那个应该学过吧，对不对 ？A 和 C 把它变成的多少张数就变成那个duality，对不对？那个 duality 嘛。不要你在这个 part one 说了 duality， 对不对？observability controllability， 对不对？有一个方法就是你如果做 full order 的话呢，那就有个方法就是还有reduce order， 对，那个我下周会讲。OK， 你如果不那么做的话，当然你无穷都会讲了，就是但是 observer 可能会不知道 ，observer 的影响不会是太影响。那你前面那2个都做出来了吗？啊？
说实话，我是用那个，我当时解决这个方法的初级取巧，我是用那个麦塞尔文内置的类似函数。
我知道你类似函数的都要你说你还是够写出来的。
哦，对，我用就是如果用。
但是你类似函数你做出来了吗？他能够就是用满足
对，
要求是吧？
那个要求我是不是？那要求。
对啊，那你还得调。
对，
你要调你的那个。
对。
OK。